We just finished roughing out this part using the solid and volume mill. It's time to finish this part now, and we have some interesting ideas on how to finish a solid. It's much easier than using two-dimensional geometry. Let's go back to our finishing end mill, and by the way, let's select contour. On this finishing end mill, let's use a 0 radius on the bottom. Here we have a plain contour. Our RPM volume mill told us is 5100, and we're going to use 30 inches a minute feed rate for entry and 60 inches a minute feed rate for finish, and we will get a beautiful smooth finish. There is such a thing as cutting too slow with your feed rate, and GibbsCAM will help you with your finishing feed rates. We have our entry-exit line radius so that we turn on cutter compensation. Without the line on an entry or exit, cutter compensation will not be turned on. We also use a radius to have a smooth transition onto the part. Our stock is going to be 0, and our overlap is going to be 0. We'll talk about overlap in just a few moments. The top of this toolpath is starting at the top, and we're going all the way to the bottom. So the top of the toolpath is 0, and the bottom of the toolpath is minus 1.280. We want to go a little bit below the part so that when we flip it over, we can face it off and not leave a sharp edge. Let's set our entry and exit clearance plane to 0.1 and 0.1. And let's set our Z-step desired as OK. Retracts, depth first, prefer subs, OK. Ramp down, no. Back and forth, no. Cutter radius comp on, coolant, no, because this is a ferrous metal part. Now, how do we cut the part? If we simply click on the part and do it, we will get a tool path. And look, it cut everything that it found. But what if we want to separate it out and just cut this section? Let's turn on this tool called the Profiler. It has 4 modes: slice plane for milling, slice plane for slice spun body for turning, slice silhouette for more complex solid models, and slice cylinder for XY type work on milling turn centers. We're going to select slice plane, and you now see a green grid. Grab the green grid by one of the grid lines, and you can move the grid up and down in the part. Wherever you drop the grid, you now have geometry that is ready to be machined. Instead of selecting the geometry and extracting it, we no longer need to clutter up our part files with a lot of unneeded geometry, because the Profiler does it all for us. One warning about using the Profiler is make sure that you don't drop the Profiler in the middle of a chamfer or a radius, because if you do, you will get the wrong size geometry. So let's drop this right in the middle of the full width of the part. Click here on the outside, and notice that the circles are gone. The circles are gone because this Profiler has automatic feature recognition, and it knows inside from outside. Let's click redo, and now we have one toolpath on the outside of the part. We said we were going to go back and talk about overlap. Overlap simply means that when we have an entry line, which turns on cutter comp, and we have an entry arc so that we gradually and gently move into the part, and then we go all the way around the part, and we depart here where the 2 arcs meet. This is going to leave a little witness mark. We want to get rid of that witness mark by adding an overlap of, let's say, 50 thousandths. When we press redo, you can see now that we lead on with the line. We arc onto the part smoothly. We cut all the way around, and then we pass the start point and lead off the part. This eliminates the witness mark here on the part if you have a nice tight machine with a nice tight spindle. Now, we're going to use this process to finish the rest of the part, including the chamfers. Let's drag the profiler up into the part where we can see the full body of this step, and let's change this minus 1.28 to minus 1. Can we get those dimensions directly off of the solid? Yes. Double click here in the bottom Z of the toolpath field, press your Alt key, and you can see that your interrogator cursor is now up. Click on the surface, and that surface has been added here into the bottom of this toolpath Z. When we press Do It, we get a toolpath. Notice that the toolpath is not affected by the height of the profiler. The profiler simply gets the geometry for us so that we can make the cuts. Now, let's go up and get the two bosses on the top of the part. Can we cut both of those bosses at the same time by control clicking? The answer is yes. But we made an awful mess of this. Our Z depth is still at minus 1. We can change our mind very quickly by double clicking here, Alt clicking on the Z minus 250 surface, and clicking Redo. We now have our chamfers cut on the part. But let's go look and see what we've done so far, and let's see what everything looks like. Why weren't the chamfers cut on the top of the part? Because we haven't designated the chamfer cut on the top of the part yet. And we're going to do that now with the finishing tool or the countersink tool. But let's go back and check in OpSim, and let's watch everything run from start to finish. Again, see it before you machine it. Face mill, volume mill, roughing, finishing. The complete outside of the part is now finished. You can see that we have some red marks on here, but they're only shadowy red marks. It means that we are exactly on the surface. If it was deep red, we have undercut the part. If it were still yellow, we have left material on the part. We'll talk a little bit about the Analyze Cut Part tool later as we get through the roughing and finishing of this part. Now that we're into the finishing, we're ready to cut the chamfers here, 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 and here. And we're going to use our countersink and the same contour process. Let's look at our countersink. We have a 3/8 countersink here. It has a 0 diameter at the bottom and a 1/87.5 or 3/16 usable flute height. And this is a 3/8 diameter with a 90-degree angle, which means that the angles here are 45 degrees. We're now ready to cut the chamfers on the top of the part. Here, we're going to bring tool number 4 into that existing contour process because we can use all of the current information. We need to change this. We know that the usable height of the flute on that countersink is 3/16 of an inch. But we don't want to go to minus 3/16 of an inch because the bottom of the tool would hit here. Let's go back and look at the drawing for a second. And our drawing says that these are 50 thousandths. So if we make this minus 0.05, we still have another problem. We're cutting with the exact tip of the tool, and we're going to leave a nasty mark on the part here. Let's drive the cutter minus 0.07. Remember, we have a usable flute height of minus 3/16. The next thing we're going to do is to set the stock plus or minus to minus 50 thousandths. 50 thousandths is the width of the chamfer. We can click on the geometry again and click Do It. And again, we define the top of the chamfer, the bottom of where we want to drive the tool, and it has to be greater than the height of the chamfer. And then we drove the cutter into the part by putting a negative stock value. When we go into Machine Sim or OpSim this time, we're going to make a change, because if we rewind right now, we go all the way back to the beginning of the simulation. In GibbsCAM 2022, click the stop sign and click Start at Operation. And we want to start at Op 9. Double-click here and select 9 from the pull-down list. Notice now that in GibbsCAM version 2022, it generates the stock immediately. In previous versions of GibbsCAM, GibbsCAM had to cycle through the stock one time to create the initial stock. Now, whenever we press rewind, we go to the beginning of Op 9. Let's slow down our throttle and next feature, which is our single block. And let's watch and make sure that everything looks okay. We're looking to make sure that we're not using the top of the tool and the bottom of the tool, because we don't want to leave a mark on the part. We just cut that chamfer, and now we're going to single block through the other chamfer. All done. Now the chamfers are cut. It's time to cut the chamfers on the top of the holes. Can we use the same process? Yes, we can. We're going to use the same depth here, but we're going to change the stock minus to minus 0.02 and click Do It. You'll see now that we have 2 new chamfers here. When we do the 1-inch hole, let's drag the profiler into the 1-inch hole. And remember, when we're doing chamfers, make sure that the profiler is on the full diameter and not in the chamfer. We set the top of the tool path at minus 250. Double click here, press your Alt key, minus 250. And then we're going to drive the minus 250 down another 70 thousandths. Minus 0.25, minus 0.07 equals minus 0.32. Click anywhere on the circle that bounds the inside of that 1-inch hole and click Do It. We have a tool path. Everything looks okay, but let's run the simulation and see what's going on. Again, before we go into OpSim, select the part, go into OpSim, and we are going to start at Op 13. We'll change this to 13. Okay, and the stock is automatically generated now. With single block, we'll go to next feature and watch it cut. And let's go here. And you can see that we have an issue right here. And the issue is that the cutter is not deep enough into the part, and it gouged the part. How can we fix that? We're going to fix that by driving the cutter farther down in the part. Right now, we did a minus 250, minus 70 thousandths. How about minus 0.250, minus 0.150 equals? And then press Redo. Now that we've done a redo here, let's go to select the part and to OpSim and click the Do It button. And now we are no longer cutting the edge of either one of these bosses. We now have one more chamfer to cut down here on the bottom, and we're going to use the exact same technique that we used before. We're going to set this to the top of the surface. We're going to use the Alt key interrogator to get that -1. And remember, this is -1, minus 0.150, because we don't want the side of the cutter to hit the side of this part. And the chamfer is -20. Let's bring the profiler down into the full diameter of the part, the full profile of the part, and let's check our parameters here and click Do It. There is our last toolpath. When we go into Sim this time, we're going to watch it again all the way from the start to see if we have missed anything. Because Analyze Cut Part and the simulation of stock inside of transparent stock is going to give us a better view of what's going on. We're going to speed up the simulation a bit so we can watch this part cut. Top step, bottom step, inside, outside, bosses. And if we go to Analyze Cut Part, you can see that we have no undercuts on the part body. If we did, they would be shown in deep red. Now, let's check for remaining material. Click Remaining Material and Show. And it looks like this is okay because it's shaded blue. This is okay. This is okay. That's fine. That's fine. That's fine. But look, we forgot to cut the holes out. So this Analyze Cut Part is a tremendous part of machining by solids. Because if you have a little tiny part with lots of little features on it, you want to check for undercuts and remaining material because we don't want to send those mistakes out to the floor. Now that we have a solid model, we want to drill these 3 holes. And drilling with solids is very easy. Click on the solid model. Select Features. Select Hole Manager. And run AFR. AFR is Automatic Feature Recognition. When you turn on Show Holes, you will see that each hole has a green stick in it right now. That is called hole data. The hole data tells us everything that we need to know about that hole. What the depth is, what the chamfer height is, what the diameter is it a through hole or a compound hole? In this case, it's a simple hole with a chamfer on it. We've already done the chamfer. Let's get our insert drill and let's cut these 2 holes. Our insert drill is a 5/8 insert drill with a 180-degree point, so it does not require a spot drill. Bring it into the process list and select holes. Now, instead of filling in all of this data, let's go to Hole Feature and set our R level from Hole Feature. At Op End, same as R level. Top surface Z, top of hole. Feature depth Z, bottom of hole. Machining coordinate system from Hole Feature. Transition between holes, R level. Now, we don't need to know anything about these holes because GibbsCAM does. We did know that we grabbed a 5/8 drill, and when we click Do It, the holes are now drilled. Let's take a look at that in OpSim, and let's start at Op 15. Let's turn our stop sign back on, and the value of 15 for our starting op. Single blocking through here, you can see that we've cut these holes. This is called automatic drilling in GibbsCAM. We're going to do the same thing with a 1-inch tool. We have a 1-inch tool here. It's a 1-inch insert drill. We're going to drop it on the current process, and guess what? We don't need to change any of the parameters of this process except for the feed and speed, because it is set to Hole Feature and all of these are automatic. When we click on this little stick here, the Hole Data stick, you'll see that GibbsCAM automatically placed the R plane, the top of the hole, and the bottom of the hole in the correct place. And if we rewind here and single block, or let's just run this in simulation, run mode, drill, drill, drill. You can see that GibbsCAM drilled these holes automatically with the proper depth. In the Hole Manager and drilling in GibbsCAM, this works on 3-axis machines, 4-axis machines, and 5-axis machines. So even if you don't know the angle or the placement of the holes on a 5-axis part, GibbsCAM can find this out for you. This part is now finished machined, and we'll do one more Analyze Cut Part, undercuts on part body, good. Remaining material, good. And most important, remaining material change. Anything that's green is complete. The advantages of machining from a solid model are tremendous. Thank you for watching this tutorial.